Welcome all first year students. I am going to take you online classes. I am handling unit 3 of your electronic subjects. In unit 3 we start from transistor biasing. I have given already the session 1 and the PPT 1. First you go to the session 1 PPT 1, under which we are studying transistor biasing and DC load line and operating point. Operating point. This DC load line, operating point and biasing are very important for all electrical and electronic circuits. First we shall discuss what is meant by bias. All electrical and electronic circuits we design for our required function. In order to get a required function in proper way, all electrical and electronic circuits needs energy or power. Both are same. Power means P is equal to VI from Ohm's law. Power equals P equals V into I from Ohm's law. Here power means both voltage and current. Biasing the circuit means giving energy or power to the circuit so that it works properly. It satisfies our desired function. For that we need to supply power. This power is a DC power, direct current power. In electronics there is a device which will supply power to the electrical circuit for its work. This power supply is regulated power supply. That is, a power supply is a device supplies a constant power to the circuit. Constant power to the circuit means P equals VI. Therefore, it supplies voltage to the circuit and hence current I flows in the circuit. When a proper voltage flows is applied to the circuit, a proper current flows in the circuit and thereby the circuit works for our desired conditions and for our desired functions. Therefore, in general, we can define biasing the circuit means supplying power to the circuit for its proper working. Now, we are discussing about transistor biasing. So, before going to transistor biasing, you should know what is meant by a transistor. And you will study the transistor in detail in second unit. However, to start, I have to give you some explanations about a transistor. Transistor is a 3-terminal device. So I will represent this as N material, P material. NP is a diode. Another P material and N material. Another diode. NP and NP. NP in this direction. NP in this direction. Two diodes NP and NP are connected back to back to get 3 terminals. And these 3 terminals are called emitter, base, and collector. So, in this transistor, N region is emitter, collector region is emitter, base region is P. Electrons are the majority charge carriers in N material, holes are the majority charge carriers in P material. Electron will carry negative, holes will carry positive. When an NP is connected, there exists a barrier at the junction. This is a junction and this is a barrier. This is a barrier. Therefore, for N material, positive ions are collected here, and for P material, same quantity of negative ions are collected here. Therefore, you get some voltage here. This is called barrier voltage. Because of this barrier voltage, free electrons which are negative charges here cannot cross this junction, because while traveling here they are repelled by this negative back. Similarly, holes here carrying positive charges, while traveling here they are repelled by this positive terminals back. Therefore, no charge carriers can cross this junction, and hence no current flows in the external circuit. This barrier acts as a closed window or closed door. Only when the charge carriers travels from N material to P material, that is, it crosses the junction, current flows in the electrical circuit or electronic circuit externally. For this reason, you have to cancel the barrier. To cancel this barrier, you have to apply, this is a positive voltage, this is a negative voltage. You have to make this NP, that is emitter and base and collector. Emitter base forward bias, that is apply external battery, negative connected to emitter and positive connected to base, so that this positive is cancelled by this negative and this negative is cancelled by the positive. Thereby the door opens, barrier get cancelled, and charge carriers can easily cross the junction and current flows in the circuit. Okay, now you see this negative terminal, this are having negative charge carriers. They are repelled by the negative terminal and cross the junction. This current flowing through the emitter to base is known as emitter current, denoted by IE. Now, to make the output current to flow here the free charge carrying negative charges, which are electrons, they are majority charge carriers in N material. These electrons must be emptied, because this portion has to collect charge carriers from the emitter. From here to it has to collect the charge carriers. Therefore, the electrons which are already exist carrying negative charges must be emptied. To do so, these negative charges are connected to external positive of the power supply. Here in this middle region P, holes are the majority charge carriers which are positive. Therefore, it has to be also made empty, and therefore it has to be connected to negative terminal of the battery. When the battery is connected in such a way that positive is connected to N region and negative is connected to P region, it is called reverse bias. So in reverse bias, since all the electrons attract here and all the holes from the middle portions P material attracts here, no charge carrier can cross this junction. Therefore, the collector current is almost zero. However, there is a small current due to minority charge carriers. You will discuss it in Unit 2. That is, current is very small. Again, from Ohm's law, R is equal to V by I. When current is very, very small, ratio is very, very large. Therefore, during the reverse bias, the resistance offered by this material is very high. that is called reverse resistance. Okay, so what you have to understand is transistor is a three terminal device, NPN, sometimes PNP is also three terminal. Okay, now let us study about transistor biasing. So the symbolic representation of a transistor is this is symbolic representation of a transistor. It has three terminals, namely emitter, base and collector. The arrow mark shows the terminal is emitter terminal. There are two types of transistors, NPN and also PNP, where the arrow mark at the emitter is inside. This is PNP transistor. However, in NPN transistor, the arrow mark is outward at the point emitter. In PNP transistor, the arrow mark is inside at the terminal emitter, base and collector. You know that for any voltages there must be 2 points. One is higher potential, another is lower potential. Lower potential is referred as ground potential. Therefore, for applying voltages to the transistor to work in a proper condition, you need minimum 2 points. But the transistor is a 3 terminal, and therefore we need 2 terminals for input voltage and 2 terminals for output voltage. Therefore, what we do is any one terminal is made common for both input and output. I will write the NPN transistor such that this emitter is common for both input and output. Now you see, there are 2 points for applying voltages to the input, and there are 2 points for applying voltages to the output. Okay, see, now the main function of the transistor is to amplify the signal. Our required function of a transistor circuit such that it should amplify our voice signal. Example, if the signal is very small and you cannot hear the sound, therefore it has to be amplified, and when you apply this small signal to the input of the transistor, output is a very large signal, that is amplified signal, and there is a phase change of 180 degree depending upon which configuration you use, your emitter configuration, because it is made common for both input and output. This is 0 degree, this 180 degree, this is 2 pi. You see, it's the amplified signal starts from 0 itself. Therefore, there is no phase difference. But in common emitter mode, what happens? If you apply positive cycle as input, you get a negative cycle as the output. That means this starts from 0 and this is pi. See, there is a phase difference here, 0, here pi. Therefore, there is a phase difference of pi. Whatever it may be, our main function of the transistor is to amplify the small signal into a large signal. To do so, the transistor has to be activated, or this transistor has to be energized. And you know that the transistor transfers the signal from a low path resistance to a high path resistance, because the input of the transistor, here base, emitter and collector are 3 terminals. Base emitter is referred as input of the transistor. Collector emitter represents the output of the transistor, and the transistor will transfer the signal from low path resistance to high path resistance. To get low path resistance, this is an NP diode and this is another NP diode. So NPN, two diodes connected back to back, refer to a transistor. Therefore, base emitter must be forward bias to get a small resistance path, and collector emitter should be made reverse bias to get a large resistance path. So, making the base emitter, that is input of a transistor, forward bias, and making the output of a transistor, here it is collector and emitter, reverse bias to achieve low resistance path here and high resistance path here. You had to apply forward voltage between these 2 points and reverse voltage between these 2 points. These supplying the voltages is called transistor biasing. Now I will show. So transistor biasing is defined as making the input of a transistor forward bias and output of a transistor reverse bias. These voltages must be derived from same power supply. You can make this forward bias and you can make this reverse bias from a single power supply. To make it forward bias, P is positive, therefore you have to connect it to a positive of a power supply. E is negative, N charge, therefore you have to connect to a N. Then it makes forward bias. To make it reverse bias, since N should be connected to positive. Emitter is N and you connect negative here. All the electrons are attracted here. Therefore it is a reverse bias. Here the holes are repelled and cross this. This constitutes a base current IB. Whatever and this is a N charge material. These electrons here are repelled by the negative terminal and flows through the base into the collector. This constitutes collector current. Therefore, transistor bias means making the input of the transistor forward bias and making the output of the transistor reverse bias so that the transistor works in a proper condition. Now, let us study about DC load line. Why this is very important. Now let me consider a general transistor circuit. I will consider NPN transistor. Okay, this is emitter, this is base, this is collector. And base emitter is made common for both input as well as output. And you know that the voltages are always applied through a resistor. Otherwise, the current is very large. Therefore, voltage must be applied always through a resistor. Now, I have to apply a voltage to this base such that it is forward bias. And I have to apply voltage to the collector such that it should be reverse bias. For that, I will connect a resistance to the collector and also resistance to the base in order to apply voltages to the base and the collector. So voltages are applied always through a resistor. Since this resistance is connected to the collector, I will call this as RC, collector resistance. Since this resistance is connected to the base, I may call this as base resistor RB. Again, to get the voltage between base and emitter, this makes this forward bias. And when N material is connected to P material, there exists a barrier between N and P junction. I will represent this as base emitter barrier voltage. So usually 0.7 volts for germanium and 1.2 volts for silicon. This is for germanium transistor. This is for silicon transistor. Now I will consider only a single power supply. I will make this base emitter forward bias. Since it is P, I have to connect it to a positive of the power supply. And this is output of the collector. And also, since this collector, this is connected to positive, therefore positive voltage appears here. This is connected to positive, therefore positive voltage appears here. P is connected to positive, here N is connected to positive. Therefore this becomes forward bias, this becomes reverse bias. That is how you have to bias the transistor. Input is always forward bias, output is always reverse biased. These forward biased and reverse biased are provided by a single power supply. Now negative is connected to 0. Now see, now the transistor works in a proper condition. Why this transistor is connected in this manner? In order to amplify the small signal. When I apply small signal to the input, you get a very large signal at the output. That is amplification, or increasing the strength of the signal is called amplification. In order to do the function of this transistor, to increase small signal into a large signal, it has to be energized by a power supply. This power supply is connected to the collector. Therefore, I will call this simply as voltage connected to collector, VCC. This is general circuit. Now to study about DC load line, I will write a circuit of a transistor amplifier. This is a resistance connected to, this is a resistance RC. This is resistance R1 or simply RB. Okay. This is our input. This is plus minus this. This is our forward voltage applied here. Consider this. Instead of writing the power supply positive to here, negative to here, it is a common way to write like that. Write like this. This is plus VCC. The positive of the power supply is connected to here. The negative power supply is connected to the ground. And we will not mention the power supply. This means shows that positive of an external battery is connected to this collector and negative of that battery is connected to the ground. So the lower point is always represents ground. This is our output. When you apply a small signal here, you get a large signal here. To do so, it has to be biased. Now this transistor is biased by the battery DC power VCC. It is called power supply. By the same power supply, you make it forward bias and you make it reverse bias. This is because this is NPN transistor. When N connected to positive, it becomes reverse bias here. When P connected to positive, it becomes forward bias here. Okay. Now, because of this power supply, let IC is the current flows through the base. And because of this forward bias, let IB is the current flows through the base. Once the input current IB flows, the collector current also flows. Now, here the voltage drop across RC from Ohm's law, V is equal to IR. Therefore, voltage drop across this is say VC, collector voltage, is equal to current into resistance, IC into RC. From Ohm's law, V equals IR. Here we have taken collector current as IC, collector resistance is RC. Therefore, voltage drop across RC is VC, collector voltage equals collector current into collector resistance. Now this is collector. This is emitter. Therefore, voltage between these is represented as, say, VCE, collector emitter voltage. It is important to note that you cannot select any value of IC. Similarly, you cannot select any values of VCE. You have to select the values of VCE such that the value of collector current IC in such a way that this is properly forward biased, output is properly reverse biased. This is called transistor biasing. Now this circuit can amplify small signal applied here to a large signal at the output. Now let us study about DC load line. Now what is the voltage applied between this point to ground point? That is VCC, power supply negative. Therefore, the voltage from here to here is VCC. From this figure, you can see that applied voltage between the collector and the emitter VCC is equal to VC plus VCE. VC plus VCE. Again, VCC is equal to, from Ohm's law, RC is collector resistance, IC is collector current. Therefore, voltage drop across this is VC equals IC RC. Substitute here. VC equals IC into RC plus VCE. You can call this equation 1. Now later on we will study the characteristics of a transistor. Here this emitter is made common for both input and output. It is an emitter configuration. Later we will study the characteristics of this common emitter configurations, and I will write the characteristics here, how it becomes. This is y-axis, this is x-axis. Along x-axis we consider the collector emitter voltage, and along y-axis we get collector current IC. A graph plotting the output current IC along y-axis, output voltage VCE along x-axis is called output characteristics of a transistor. For any one base value current constant. You will study it later. I will write how the characteristics will appear. The characteristics will be, first, when VC increases, it increases and then remains constant for a long length, for some length of VCE, and after some VCE again it increases. These characteristics of three portions, these increasing portions, almost constant portions, and again increasing highly due to avalanche effect, we shall study it later. This region is called breakdown region. This region is called cutoff region. Cutoff region. This is called constant current. Here the independent of VCE, because even when VCE increases, there is no rise in current, it remains constant. This is called saturation region of the transistor characteristics curve. So one cutoff region in which the current is almost 0, and another portion in which the collector current IC remains constant. It is independent of increase in voltage, and after certain value of VCE, above VCE, it increases suddenly. That is, it is called breakdown region. This is called breakdown region. Now, DC means direct current. Therefore, it is a constant current. That is, it is a straight line. There is no variation. Therefore, a straight line such that this cuts the y-axis at some point and x-axis at some point, and also that straight line cuts the characteristics at some point. This is called DC load line. Let us show how the DC load line is obtained. So this is the equations. Here VCC, this is equal to VC plus VCE. VCE means ICRC from Ohm's law. IR is voltage, and here the voltage is VCE. And I have represented this as x-axis, taking IC as y-axis. Take this IC. Therefore, from this equation 1, ICRC is equal to VCC minus VCE. Dividing throughout by RC, we get dividing throughout by RC to get Y form. IC is Y. We get IC is equal to dividing by RC. RC get cancelled. Here you get VCC by RC minus VCE by RC. I will rearrange this term. IC is equal to, I will write this as minus 1 by RC into VCE. Just I will rearrange. So 1 into VCE is VCE itself. So VCE by RC minus. This is plus VCC by RC. IC is taken in a y-axis. VC is taken in a x-axis. Therefore, I will represent this as y is equal to mx plus c, where constant c equals VCC by RC. And m is the slope of this. This represents a straight line. M is the slope of the straight line. Here compared to this, the slope of this equation is minus 1 by RC, because instead of m, there is minus 1 by RC. Instead of c constant, there is VCC by RC. Therefore, in the above equation, m is minus 1 by RC and the constant c is VCC by RC. Okay, now let us consider the point on y-axis when x-axis is 0. When x-axis is 0, you get only y-axis. Similarly, when y-axis is 0, you get only x-axis. Consider this point. Here x-axis is VCE. So when VCE is 0 here, 0 into anything is 0. First case when VCE equals 0. From this expression, minus 1 by RC into 0 is 0. Therefore, IC equals VCC by RC. You can call this point as A. Therefore, when x-axis is 0, you get a point A where the value of IC is equal to VCC by RC. Okay. Now, when y-axis is 0, see in these equations, y-axis 0 means IC is 0. When IC is 0, VCE equals VCC. Therefore, when there is no current, this VCE is equal to VCC. When this is 0, VC equals VCC. Mark that point. Let this point be B, where the value of VCE is VCC. Thus, you get 2 points A and B. Join A and B because y equals mx plus c is a straight line. That means IC equals minus 1 by RC VCE. IC equals minus 1 by RC VCE plus VCC by RL RC is a straight line. Therefore, join A and B. You get a straight line. This is a DC load line. How do you define DC load line now? It is a straight line cutting the y-axis at maximum collector current, which is given by VC by RC, and cutting the x-axis at maximum collector emitter voltage that is given by VCC. So this is called a DC load line, and slope of this is C here, M equals minus 1 by RC. Therefore slope of this curve is minus 1 by RC. Why negative sign? When voltage increases, current decreases. Therefore it is a negative slope. Okay. Now let us study about operating point. Operating point is very important. This operating point, that is the C amplifier, should work in proper way, selecting the values of voltage and current of a transistor such that it should produce a faithful amplification. Selecting that voltage and current of a transistor is given by operating point. This is also called quiescent point. QUICENT, quiescent point. Then what is operating point? You see this curve. This is a characteristics curve. This is a DC load line. And you get a point of intersection here. This point of intersection of a DC load line, and for any one given characteristics, output characteristics of transistor, this is called operating point. At this operating point, note down the voltage. I will call this as collector emitter voltage. Collector emitter voltage at operating point. At this Q point, note down the current. This is the current. That is the collector current at operating point. Therefore, Q into Q within bracket, voltage at this point is, here to here it is VCEQ, from here to here it is ICQ. This is called operating point. So operating point is the point of intersection of a DC load line and output characteristics of a transistor, so that the proper value of collector emitter voltage and the proper value of collector current are taken. And this operating point changes whether the entire input signal has to be amplified. Suppose this is the signal, this is an amplifier circuit, and the operating point depends, Q of the circuit, operating point of transistor depends upon whether only one cycle is conducted at the output or the entire cycle is conducted, or only a portions of this should be conducted. When entire signal is conducted, you get an enlarged signal like this. Only one portion's half cycle is conducted, you get only half of cycle is amplified. You get a portions, only portions is amplified. Depending upon this, whether full cycle is conducted, half cycle is conducted, or portions of either positive or negative cycle is conducted, we will select the values of VCEQ and ICQ. This is done by Q, the operating point, and we shall discuss it later. Operating point. Thank you.